This presentation treats the Hilbert Book Model project. The target of the project is the generation of a mathematical model that can be used in order to investigate the structure of the foundation and the lower levels of the structure of physical reality. I am a retired physicist. I spent my career in high-tech industry.
This lecture introduces you to the Hilbert Book Model. The model deviates considerably from the models that constitute contemporary physics. The model is strictly based on a trustworthy foundation. The Hilbert Book Model selects Hilbert spaces for that purpose. The model applies a system of Hilbert spaces. These Hilbert spaces all apply the same underlying vector space. The Hilbert Book Model represents my personal view on the lower layers of fundamental physics. A quaternionic Hilbert space can easily be structured as a dynamic model in which all past, present, and future geometric data are stored. Therefore, the corresponding space progression model becomes paginated like a book. It consists of an ordered sequence of static submodels. That is why the project got its name Hilbert Book Model. Please look at the book or paper, The Setbacks of Theoretical Physics. This is part 3 of a multi-part presentation on the Hilbert Book Model. This part concerns the third phase of number systems. New items are formulas that became famous in literature and represent combinations of continuity equations and balance equations. Both mathematics and experiments are covered. Experiments use physical units. In the third phase of number systems, all convergent series of numbers end in a limit that is a member of that third phase. This fact enables the differentiation of the third phase. Differential calculus shows that the third phase can change. The third phase shows astonishing behavior. It has the habit to remove deformations. Without disturbing actuators, the third phase stays flat. For enclosed regions, the continuity equations that hold inside the enclosure relate to the balance equations that consider the transfer through the boundary of the enclosure. The relation is that the quaternionic spatial del operator is replaced by a normed spatial number that represents a part of the boundary. The relation is that the quaternionic spatial del operator is replaced by a normed spatial number that represents a part of the boundary. The balance equation then takes the form the quaternionic equivalence of Ampere's law, R. Ampere's circuital law relates the integrated magnetic field around a closed loop to the electric current passing through the loop. James Clerk Maxwell, not Ampere, derived it using hydrodynamics in his 1861 published paper on physical lines of force. In 1865 he generalized the equation to apply to time-varying currents by adding the displacement current term, resulting in the modern form of the law, sometimes called the Ampere-Maxwell law, which is one of Maxwell's equations which form the basis of classical electromagnetism. Maxwell's equations are experiment-based equations and use physical units. The equations and enable the derivation of the Lorentz force. This derivation applies the Leibniz integral with and follows. The electromotive force, EMF, equals. Thus, this is the equation for computing the Lorentz force spatial F. The famous equations indicate that quaternionic field equations were developed by mathematicians and used by experimental physicists independent of the discussions of Hilbert, Cantor, von Neumann, and Zermelo that concerned set theory. Maxwell's equations were checked experimentally and formulated by using physical units. Compared with quaternionic field equations, the first-order Maxwell equations missed the real part. This was used by physicists to introduce a gauge. This gauge was applied as a renormalization. The quaternionic field equations do not need renormalization. Hilbert, Cantor, von Neumann, and Zermelo discovered the continuity hypothesis, but did not discover that continuums are part of a special set. That set exists in several phases. These phases can be changed by phase transitions. The phase transitions cannot be achieved in a step-by-step way. Hilbert, Cantor, von Neumann, and Zermelo never considered that possibility. The Hilbert Book Model embraces the special set. Primitive space acts as a container for the special set. Locations are the elements of the special set. Locations are point-like objects that tell a position in primitive space. That position can be indicated by the value of a member of a number system. This is treated by Part 1. This ends Part 3 of a multi-part presentation that concerns the Hilbert Book Model. This part concerns the third phase of number systems. New items are parts of change that compensate each other, tricks that work in isotropic conditions, and new second-order partial differential equations. Part 4 will concern Hilbert spaces and systems of Hilbert spaces.